Hey everybody, welcome back to another lecture video. This time we are looking at chapter 13, and chapter 13 is all about solutions. So let's just jump right in. I'm going to tell you guys a little story. In late summer of 1986, carbon dioxide bubbled out of Lake Neos. Now, this is a picture of that, Lake Neos, and flowed into the valley that was adjacent. And so this carbon dioxide, it came from the bottom of the lake, where it was held in solution uh, by the pressure of the water above it. So if you think about a lake, right, you've got all of these bubbles, right, or all of this dissolved gas was actually being held in there by the pressure of the water. So we know about air pressure. Water pressure, too, we know it has the same effects, at least in terms of the volume and pressure relationships. And so, anyways, the layers of the water were actually holding all of this carbon dioxide. Now, the carbon dioxide was coming from a volcano. And when these layers in the lake got disturbed, the carbon dioxide came out of solution because of the decreased pressure with some lethal consequences. And so this lake was actually a water-filled volcanic crater, so as I mentioned, and this volcano was producing carbon dioxide gas that was seeking through sort of the volcano's plumbing and getting into this water. And so the concentration of carbon dioxide built up in the water, and it can actually increase with increasing pressure. So just like we saw, actually we didn't see, I was going to relate it to water vapor or the temperature dependence on vapor pressure of water, but actually it's quite different. So think of a soda, a flat soda versus a non-flat soda, right? If you leave your soda can uncovered or your soda bottle uncapped, it'll go flat. If you leave it capped, right, it stays carbonated. And that's because the pressure inside a closed container keeps it from basically going flat. And so the greater pressure at the bottom of the lake allowed for this carbon dioxide concentration to build up very high. And then over time, carbon dioxide and water at the bottom of the lake became so concentrated that some of the gaseous carbon dioxide started to escape. So it started to turn into bubbles and come out. Now, the rising bubbles disrupted these stratified layers of lake water and caused the highly concentrated carbon dioxide and water mixture at the bottom to rise. And so turbulence, basically, in the water caused all of this water down here that has the CO2 in it to start making its way up to the surface, or at least just, coming up a little bit where the pressure was less. And then it was like a chain reaction. The drop in pressure on this mixture just released more carbon dioxide bubbles. Long story short, carbon dioxide is heavier than air. So once it was freed from the lake, it just traveled down the sides of the volcano and into that nearby valley, and it displaced all of the regular air. So because it's heavier and denser than air, it just pushed all the regular air out of there. And so about 1,700 people, 3,000 heads of cattle, all died, suffocated. And so, this tragedy was a result of solubility of gases and pressure. And so by understanding these things and to prevent these things from happening in the future, scientists have built a piping system that actually slows down the carbon dioxide buildup by venting it out of the lake. And this system has been gradually releasing carbon dioxide into the atmosphere so that it doesn't build up in the water. And that's kind of what I'm showing you here. So the controlled release of the carbon dioxide from the lake bed, designed to prevent future catastrophes. Okay, so the carbon dioxide and water mixture at the bottom of Lake Neos is an example of a solution. And again, this is what this chapter is all about. So a solution is a homogeneous mixture as opposed to a heterogeneous mixture of two or more substances. Now, solutions are common. Most of the liquids and gases that we encounter every day are actually solutions. The ocean's a solution of salt and other dissolved solids in water. Blood plasma, for example, that has had the blood cells removed, is a solution of several solids as well as some gases dissolved in water. So a solution can be composed of a gas and a liquid, like the carbon dioxide and water of Lake Neos, or a liquid and another liquid, such as ethanol, or alcoholic beverages. We have ethanol, the main sort of alcoholic ingredient, the inebriating ingredient, and then water. They can be solutions of solids and liquids, so like salt water or sugar water. They can be solids and solids. We don't think of those too often, but alloys like brass or iron. Sorry, not iron, steel. These would be solutions of solids. But more commonly, we think of solids and liquids, gases and liquids like carbonated water, or the fact that fish can breathe in water. That's because there's dissolved oxygen. Fish need oxygen too, but it's dissolved. So again, that would be a solution. And then gases and gases, or gases in gases like our oxygen and carbon dioxide and water vapor that all dissolve in nitrogen gas, or are all part of a nitrogen gas solution. Okay, so lots of different combinations in terms of what solutions can be. Now, solutions have to have at least two components. They have the solvent, and this is usually what's in the major component, with the exception of water solutions, and I'll get to that in a second. Then there's the solute. So solvent and solute, and these are the minor components. Now, technically, anytime, so again, we would just look at how many moles we have of each. So I'll give you an example. Let's do a saltwater solution, NaCl. Now, you remember aqueous is a phase that we use. Aqueous here is just to refer to water as being the solvent. Okay, that's what aqueous means, because water is so abundant on Earth. It's the very common solvent. Other solvents are used in the laboratory and the industry, and even in the home, especially to form solutions with like non-polar solutes. So we use, rubbing alcohol, or we'll use which is isopropanol, or acetone or hexane or something like that. These are other solvents, and I'll show you some solvents, polar and non-polar, here in a second. But what I'm getting at, or what I wanted to get to, is even if you were to make a solution of salt and water in such a way that you had more salt moles technically than you had water moles, so technically salt would be the thing you have more of, and it was the major component, you still would call the water the solvent. And that's just true of all aqueous solutions. That's just how we define them. We just say water is the solvent, whether or not it actually is the major component. Every other type of solution, whether those be gas-gas solutions or solid-solid solutions, or anything that isn't water, then we are going to hold it to the solvent-solute sort of rules. Okay. Now, these are some types of solvents. Whenever we're choosing what kind of solvent we want to use, we need to look at what we're trying to dissolve. And so if we're dissolving things that are polar, like ions, like sodium chloride, or potassium iodide, we'd want a polar solvent. Water, acetone, methyl alcohol, these are all polar. If I was to draw their Lewis structures, so this is acetone, this is methyl alcohol, and we know water. You can see they've got some polar attributes here. This is an OH, therefore this thing can form hydrogen bonds. It also has some polarity toward this oxygen atom, giving it kind of a negative charge. Same thing here. This carbon is kind of positive, and this oxygen is kind of negative due to the way the electrons are being pulled. Some of these are more polar than others. In fact, if we had to put them in an order of decreasing polarity, this would be the most, and this would be the least. And again, we would know this because we'd look at the types of bonds that are there. This one has hydrogen bonds, not just one, but two, and not just the ability to do two, but the ability to do four. The next molecule can do hydrogen bonds, only one, as opposed to two, so it's not as polar. And then this one here can't do any hydrogen bonds. So right off the bat, it's just a dipole interactions as opposed to hydrogen bond interactions. So we can order them in that sort of way by just thinking about the forces that exist. Now, as far as nonpolar ones go, here's just a couple that we can talk about. Hexane is a nonpolar solvent. Diethyl ether, commonly known as ether, another nonpolar type of solvent. And then toluene. Toluene, also nonpolar. These are just made up of carbons and hydrogens, with the exception of diethyl ether here. But ethers tend not to be very polar. Not as polar as, like, let's say acetone, which isn't an ether. Okay, we say in chemistry, like dissolves like. And this just means that when we are picking solvents, we want to pick a polar solvent to dissolve polar solutes, and a nonpolar solvent to dissolve nonpolar solutes. And the reason for that has to do with the interactions that take place. So the formation of solutions, especially of these dissolved solids in water, there has to be a solvent-solute attraction. And that solvent-solute attraction has to overcome the solvent-solvent attractions that exist. So in a pure sample of water, all the water molecules are attracted to each other because of their polarities and hydrogen bonds. And so coming in between those water molecules is going to take a certain amount of energy. In our solute-solute attractions, we've got NaCl molecules, right? If in our NaCl solid, and in our pure water sample, we have these forces that we have to deal with. And the NaCl, right, is held together by these electrostatic opposite charges, and that's a really strong force as well. These are going to both require energy to break. Now, where does that energy come from? The energy is going to come from the dissolving. If sodium chloride dissolves in water and forms new interactions, so by new interactions, water molecules will surround the ions instead of water molecules holding hands with each other, and instead of the ions just being paired up. If water can completely surround, the sodium ion, and water can completely surround the chlorine ion, and if that new arrangement gives off energy, meaning that they're able to become more stable, if they're able to lower their energies by doing this new arrangement, then that'll actually release some energy. That energy being released can cover the cost that it takes to separate out these guys from each other. So this is really what it comes down to. It's the, when we think of something dissolving, you remember ionic compounds like silver chloride don't dissolve in water. So there are things that don't dissolve in water. A lot of those magnesium, or a lot of those hydroxide compounds, like, what was one of them? Calcium hydroxide, was it? Possibly. These guys don't dissolve in water, even though they're ions. And so if they don't dissolve in water, it's because the new solute-solvent interaction that would come from them dissolving isn't actually strong enough to overcome the natural attraction of these ions for each other. Or, these guys they don't provide enough to the water molecules that'll let the water molecules stop holding on to each other. So those are the interactions that are kind of going on. There's the ones that hold solutes together. There's the ones that hold solutes down here. Solvents, there's the ones that hold solvents together. These are kind of endergonic forces, meaning you have to put energy in to overcome those. And then there's that new force, the solute-solvent attraction force. Now I've got an image of that. So here's salt crystals, water molecules coming in, starting to dissolve them, obviously from the outside in, and you can see that the negative chlorine ion will be surrounded by the positive side of the water molecule, and the positive sodium ion will be surrounded by the negative side of the water molecule. So you should be able to tell here that the water molecules are facing different directions when they surround these ions. So again, in Chem 1 we go into this a lot more, but the energy that gets released by compounds dissolving, if enough energy gets released, then it overcomes those attractive energies that you have to put in, those energies to break apart the solute and the solvent. And then things dissolve. But if that new arrangement doesn't or barely pays, if it barely pays the cost, it also dissolves. But if it doesn't pay the cost, if that energy that we, that new formation of this essentially isn't worth doing because it doesn't even give enough energy to actually break apart your ions, then it doesn't happen. And that's like in the case of these insoluble compounds in water. Okay, so in a solution then, in this case in a solution of NaCl, the sodium and the chlorine ions are dispersed in the water. The water molecules surround the ions, and we have our homogeneous solution. Now, we can talk a little bit more about solubility, some terms, and then we'll talk about these electrolyte and non-electrolytes. So first, solubility is a term we use to define the amount of a compound, usually in grams per 100 mils of the solvent. But it's just grams in a certain amount of the liquid, and that's how we define how much of something can dissolve. So, for example, the solubility of sodium chloride, now we have to pick a temperature, so let's just say at like 25 degrees Celsius. The solubility of sodium chloride is actually 36 grams per 100 grams of water, or 100 mils of water. To give you another one, let's say KCl might be, only 12 grams per 100 mils of water. I think I'm making up the second one because I thought I had two examples. I don't have two examples. But they would be different. So solubilities would be different. Now, they are temperature dependent, and we'll look at that. Now, let's talk about some other terms. Now, there's the term saturated. Now, a saturated solution is one that holds the maximum amount of solute under whatever conditions. So, if I had a solution of sodium chloride, and this was 100 mils of water, and according to, my solubility, at this temperature, I should only be able to dissolve 36 grams in here. If this solution has 36 grams of salt in it, then it's saturated. If I try to put more in here, if I try to add, let's say, 38 grams, then 36 grams will still dissolve. But then I'll have 2 grams of salt that sets down here at the bottom. It won't dissolve because there's not enough water to dissolve it, or the temperature's too low still. So that would be that's actually what we would call a saturated solution. It's got the maximum amount dissolved inside it. Now, we have unsaturated. Let's talk about that. So sodium chloride has a solubility of 36 grams per 100 mils. If this is 100 mils, and I've only got 15 grams of sodium chloride in here, then it's an unsaturated solution. It has not reached the maximum amount of solute that it can hold. And so I could continue to add salt into this unsaturated solution until it became saturated. Now, there actually is something called supersaturated solutions, and let's talk about that. A supersaturated solution can actually form under special conditions. Supersaturated. Now, a supersaturated solution is holding more than the solution is intended to hold at those conditions. So more solute than the maximum. Kind of like the carbon dioxide and water solution from Lake Neos example. That was a supersaturated solution because of the drop in pressure. At high pressure at the bottom of the lake, it could hold that much gas. But because the pressure dropped, because the water started to kind of swash around and get moved around because of the bubbles, then at lower pressure, it cannot hold that much gas. And so all of that gas dumped out. And so that's what happened. It became supersaturated. And so then when things become supersaturated, they essentially just become very unstable. And if it's gases, then they bubble out. If it's solids, then they crystallize out. And I've got some pictures of some rock salt to show you, because when we talk about the temperature dependence here, I'll tell you how we can make a supersaturated solution. Now, in addition to saturation and solubility, there's also some other properties that we can talk about. This isn't, well, here, let me back up. So solubility rules give us a qualitative description of the solubility of ionic solids. So if you remember the calcium carbonate, we know it's an insoluble compound. the attraction between the calcium and the CO2, CO3, Ca2 plus, CO3, 2 minus, calcium carbonate solid. This thing doesn't dissolve in water. It's because the attraction between those ions is actually greater than the solvent-solute attraction would be. And so the solubility of calcium carbonate is pretty much close to zero. It's approximately zero in 100 grams or 100 mils of water. Now, molecular solids that aren't ions can also be soluble in water, and this is depending on whether or not the solid's polar. So we've talked about ions. Now let's talk about molecules. So something like sugar or caffeine. These things dissolve in water the same as ions do, maybe not to the same extent, but it's because they are polar. Now I'm not going to draw you a structure of a sugar here. Just take my word for it. These have some very polar bonds, and then there's lots of OHs attached to the structure. There's occasional C double bond O's in there. So this is a polar group. These are hydrogen bonding groups. So water likes these types of compounds. Non-polar solids like lard, vegetable shortening, these things are typically insoluble in water. Okay, if something dissolves in water, it can be an electrolyte or a non-electrolyte. So let's talk about the difference. Now that we know that things can dissolve in water, they can be described by their solubility in terms of grams per milliliters, but they can also be talked about as electrolytes and non-electrolytes. And so an electrolyte solution is one that contains dissolved ions. And this would basically mean that it can conduct electricity. So when you put two leads, let's say here's a plug and here's another plug, and these things go to, I don't know, a battery. Electrons flow through the copper wire, right, of your electronics. But then when they get to the solution, they don't flow through the water. What actually flows through the water is that this electron, they start to build up on the edge of your electrode here and get a negative charge, which is going to attract ions. And so ions in the water are going to start to move. Now, positive ions are also going to be attracted. Positives will be attracted to the negative. This is going to be your positive electrode. Negatives will be attracted to that one. But the fact that these ions are moving means that the charge can basically flow through the whole circuit. So if you don't have ions, you can't conduct electricity. If you tried to do this with a sample of pure water, tried to run electricity through it, it would not conduct electricity. It has to have dissolved ions in it. Now, dissolved substances in general is not enough. They have to be ions. So even though these sugar molecules are polar and water does dissolve them, they do not conduct electricity. And this is because they're neutral. Neutral particles don't move because of electric currents. So a non-electrolyte solution is one that doesn't have ions in it. It should just be called an ionic solution, but an electrolyte solution has ions, dissolved ions. Now, in general, the solubility of solids in water increases with increasing temperature. So as you increase the temperature, and these are just different curves for different solids, you can see that it does have an effect on their solubility. So let's take a look at one. So let's say that at 10 degrees, right here, at 10 degrees for sodium chloride, the solubility is about, 33. We know what it is at 25 degrees, it's 36, but at 10 degrees, let's say it's 33. So at 10 degrees, the solubility is 33 grams. Now this is per 100 grams of water, so I'm going to say 100 mils. It's the same thing. Plus, if we talk like this, it'll make more sense for your lab that you do that has the same concept in it. And so the maximum amount of salt that we can actually hold, the saturated solution would be at 33 grams. Now, if I increase the temperature, let's say to 100 degrees, the solubility is actually 40. So that means if I wanted to dissolve, 7 more grams of salt into that same amount of water, I have to increase the temperature. Now here is how rock candy gets made. Let's talk about rock candy. So the recrystallization I was talking about usually happens in the opposite direction. When you take a saturated solution and then you make it unsaturated. Now, increasing the temperature has the opposite effect, right? This was a saturated solution. Let's say that I actually stuck 33 grams in here, or let's say I stuck 36 grams. I've got 36 grams of salt dissolved at 10 degrees. So in my container, right, 100 mils, I've got 33 grams dissolved, and I've got 3 grams at the bottom, right? Because I've got 36 altogether, but this can only hold 33. So then I raise the temperature to 100 degrees. Well, I no longer have a saturated solution because my solution can hold 40, and I've only put in 36, and so now all 36 grams are dissolved, and there's nothing at the bottom because those extra grams that couldn't fit in here to at that right temperature, they could dissolve at a higher temperature. So this is not when we see recrystallization. We see recrystallization when we go the opposite way. So let me give you an example. Let's say that I have a saturated potassium nitrate solution at 80 degrees. Okay. Actually, let's use our graph. So our graph here tops out right here for potassium nitrate. That's about, I don't know, 54 degrees. So let's say at 54 degrees, I have a saturated KNO3 solution. And I want to know what's going to happen to my solution when I drop that temperature to a different temperature. I want to drop it to 10 degrees. So at 10 degrees Celsius, how much KNO3 is actually going to recrystallize? And what recrystallize means is it's going to turn back into a solid. Okay, so I've got, let's see, how much can we hold in here? This says at 54 degrees, I can actually hold 100 grams. So this saturated solution right here has 100 grams of dissolved KNO3 in it. At 10 degrees, I can hold 20 grams. So there's going to be 20 grams dissolved, and then I'm going to have a bunch of recrystallized solid. I'm going to have 80 grams of it. Does that make sense? So I had a saturated solution. Saturated solution was the only clue. I had to look at my table to figure out at what temperature and at what amount of grams that actually was. So I found out that saturation meant 100 grams. Now, if I had stuck with my initial temperature of 80, you can see that this curve would keep going. There's no way to know how many grams at 80 degrees, and so this graph would have failed me there. So I had to pick a temperature that matched up with my graph. But anyways, this is how you use this table, and this is how you can find out how much recrystallizes. Now, let's say that I only had 10 grams dissolved at 100 degrees. So first, my solution would have been unsaturated, because at 100 degrees, I can hold 100 grams, but I've only put 10 grams in there. So that's the situation at 100 degrees, or at 54 degrees, or whatever. I've only put 10 grams, so it's unsaturated. Now, if I drop the temperature to 10 degrees, how much will recrystallize? None, because at 10 degrees, I can still hold 20 grams, and I've only got 10 in there. So I'm still unsaturated. I would have to drop this temperature, even at zero, this would still be unsaturated, because you can see I haven't actually reached my my solubility limit. It says my solubility at, oh wait, am I reading that right? Where's KNO3? Yeah, solubility at 0 is still like 13 grams. So even then, I'm still under the limit. So none would recrystallize. That's what I'm getting at. So as long as you're unsaturated, then nothing recrystallizes. We only get crystallization or recrystallization when we are saturated. So take a look at this. So this is rock candy. So rock candy, what you do is you make a saturated sucrose solution, a table sugar solution, at a high temperature. So you stir in sugar into warm water until it can't dissolve anymore, and then you heat up that water. Basically, you get it like almost boiling. Super hot water, you dissolve as much sugar as you can into it, and then you let it cool, and you just dangle some strings in there, and you let it cool for a couple days, and as it cools, it becomes super saturated, and the sugar crystals start to grow in the string. There are ways to get supersaturated solutions that still look liquid. So you can take a beaker. Sorry, it's a terrible beaker, and it's got, let's say, a liquid in it of supersaturated, sodium acetate, and then you pour the solution out onto like a table. And it sounds crazy. What you do is you put a little crystal of sodium acetate, and then you pour the solution on it. And as soon as that solution hits this, it's so unstable that it just lands as a solid. And you can build these really big stalagmites, like off the ground, of sodium nitrate. In fact, sodium acetate. Google or YouTube sodium acetate crystals or recrystallization, and you'll see a really neat video. I did this as a demonstration in class before, but it's kind of hard to. I didn't tape it, or I'd show it to you here. All right, so that's how that's solids with. So this is solid solubility. So for solids, basically temperature determines. Okay, and with increasing temp, we get increasing solubility. Now, with gases, it's different, okay? With gases, we know that pressure is a factor, but there's even some temperature component. So the water at the bottom of Lake Neos, right, and a can of soda are both examples of solutions in which carbon dioxide are dissolved. Now, most liquids exposed to air contain some dissolved gases, like lake water and seawater. They have oxygen, like I mentioned before. Our blood contains dissolved nitrogen, oxygen, and carbon dioxide. Even tap water contains dissolved atmospheric gases. Now, you can see the dissolved gases in ordinary tap water by heating it on a stove or leaving it in a bottle of water out in the sun. You'll see little bubbles start to form in there. Now, even when you're boiling water, right before it reaches its boiling point, you see small bubbles on the bottom of the pan. Now, these are dissolved gases that are coming out of the solution. If you were to ever use dissolved water or boiled water to, let's say, fill a fish tank, and then you put fish in it, they'll die because you've gotten rid of all the gases in that water. So let it sit out long enough, give it some stirring and stuff, and you can get gases to dissolve back into it. But flat water doesn't taste as well. Also, for us, we can actually taste the flatness in the water. So anyways, actually that's another point that I wanted to make, is that they often bubble oxygen through our water at the treatment facility to make it taste better. So as the temperature of water rises, the solubility of dissolved gases decreases. And so once the water boils, let's say when we're boiling water, all those bubbles have taken all the gases out, and then the water actually just boils and it turns into a gas. But that's not the dissolved air. We can see this better when we're looking at a warm soda. Warm soda, carbon dioxide just starts to come out. It doesn't stay as dissolved as easily, and so we see the fizz. So pressure has a component. In Chem 1, we would be dealing with this. We would be doing the math for this. We're not going to do anything here other than talk about it. So as far as gases go, there's a pressure component and a temperature component. To increase the solubility of gases, we have to increase the pressure and decrease the temperature. Okay, so the higher the pressure above a gas, then the more soluble that gas is. Think about, and so you can picture that here. So there's not as much, let's say, carbon dioxide dissolved in water, in ocean water, as oxygen. And the reason for that is because there's different partial pressures. There's not as much CO2 in the air as there is O2 in the air. And so since there's more O2 in the air, more O2 gets into the water. So this is an example of talking about how the partial pressures of each gas affects its solubility, but also just in general, if you increase the amount of a certain gas in the air, like if this was the same gas, now there's more molecules here where there was less, that's going to mean more of them end up dissolving into the water. Now we can see this effect better with the soda can, right? Under pressure, all of this carbon dioxide stays dissolved, and they actually fill the headspace of the soda can with CO2 as opposed to regular air to help keep that CO2 dissolved. Once you open the lid, all of the CO2 gas starts to flow out, and none of it stays in the top of the can, and so that just encourages more CO2 to undissolve and to flow out of your can. All right, so that's how pressure is related to it. So solubility related to temperature, gas solubility related to temperature and to pressure. Okay, now let's talk about how we quantify solutions. So specifying solution concentration is particularly important. And the first way that we're going to look at concentration is the mass percent. Now, this isn't anything new. We've talked about mass percent before, but we were doing it with atoms in molecules. We were saying something like the mass percent of sodium in sodium chloride. Now we're going to talk about something like the mass percent of sodium chloride in a solution. And so we need to know two numbers. We need to know the mass of the solute, so the thing being dissolved, and then the total mass, the mass of the solute and solvent combined. And so a mass percent is usually, so let me say this. So let's say that we have a solution that has 14 grams of solute over 100 grams of solution. So there was 86 grams of solvent, 14 grams of solute. The whole solution is 100 grams. So this times 100, that's how you do percents. You can see this comes out to be 14%. So let's say that I was given, so that's how you solve for percentages. But let's say I was given a percent. Let's say I was given that my mass percent is, 19. Mass percent of my KCl solution is 19. Well, that we can interpret to mean that I have 19 grams of solute for every 100 grams of solution. Remember every time when we were doing our empirical formulas, when we were giving a percent, like 30% carbon, we just said there was 30 grams of carbon in every 100 grams of stuff. We can do the same thing here. So if we're given a mass percent, this just becomes 27 grams of solute for 100 grams of solution. Okay, so we can do an example. So let's do an example. Let's calculate the mass percent of 41.2 grams of C12H22O11 and 498 grams of water. So we've got the solute, we've got the solvent, we need to add them together, we need to set up our mass percent. So 41.2 grams of solute over 41.2 plus 498 is 539.2 grams of solution times 100. So 41.2 divided by 539.2 times 100 is 7.64%. So this would be a 7.64% C12H22O11 solution. And again, if we were given this percentage, we could say that there's 7.64 grams of C12H22O11 in every 100 grams of solution. And we can prove if this is right or not. We know how many grams of solution we have right here. Well, actually, that would be kind of circular. But I was going to say we could take 539.2 grams of solution, and if we knew this percentage and this conversion factor, we could find out very easily. We could say, okay, for every 100 grams of solution, there's 7.64 grams of this solute. Well, this is circular math, but you can see it would give us 41.2 grams. So we can use this to find out grams of solute when we know grams of solution if we know this percentage. All right, the next type of concentration that we want to worry about is something called a molarity. Now, let's see. Actually, I do have one more mass percent that we can use in calculation. Let's talk about. Let's use an example of Lake Neos. So, water sample from the bottom of Lake Neos contains 8.5% carbon dioxide by mass. So the question is, determine how much carbon dioxide in grams is contained in 28.6 liters of this water solution. So we're given the mass percent, we're given volume of water, or I'm sorry, the volume of the solution, and they've also given us the density of the solution. The density of this water solution, or water and carbon dioxide solution, is 1.03 grams per mil. Okay, so we need to recall that there's 1,000 milliliters in 1 liter. And what we can do is we can say, with our 28.6 liters, and that there is 1,000 milliliters in 1 liter. That's backwards. One liter has 1,000 milliliters. We could say that in 1 milliliter, there's 1.03 grams of carbon dioxide, or grams of mass. We'd say for every 100 grams of solution, it's 8.5 grams of CO2 from our mass percent, right? That's our mass percent. Grams of solution cancels, mils, liters, and then we just do the math on this. This comes out to be 2.5 times 10 to the 3 grams of carbon dioxide. So using mass percent in a calculation. All right, so the next one's molarity. Molarity is defined as the number of moles per moles of solute per liter of solution. So we can set up our big M to equal moles over liters. So we have to find out the moles of our solute. We have to find out the liters of our solution. Molarity is moles of solute per liter of solution, not per liter of solvent. So keep in mind, solution, not solvent. Now, to make a solution of a specified molarity, you usually put the solute into a flask and then you add water to the desired volume. So for example, if I want to make a 1 molar NaCl solution, I weigh out 1 mole of NaCl. That's going to be about 5844 grams. So we put all of that, so 1 mole of salt, into this flask. And now these are volumetric flasks that have just one notch on them for specified volume. So this is the 1 liter volumetric flask. So then we just fill up the water to the 1 liter mark and stir. So this would be, so you don't, this inside here is actually taking up volume. So we didn't actually add 1 liter of water, right? We just made the total volume 1 liter. So that's where you want to make sure you're not thinking in terms of solvent. It's not a liter of water, it's however much water it takes to get to the 1 liter mark, and that's going to depend on how much space that salt takes up. Now sometimes because that can add to the complexity of a problem, sometimes we just say, pretend the solvent doesn't have any effect on the volume. So let's do a problem. Let's do practice. So let's calculate the molarity of a solution that's made by putting 15.5 grams of NaCl into a beaker and then adding water. Draw a picture. Into a beaker and then adding water to make 1.50 liters of an NaCl solution. So the question is, what's the molarity going to be? So we need to figure out how many moles we have. And so if you remember, moles we find from grams, using the molar mass. So we're going to say, I've got 15.5 grams of NaCl. From the periodic table, we can calculate that 58.44 grams, or I guess from this slide right here, of sodium chloride will give us 1 mole of NaCl. And so that's going to be 0.2652 moles, keeping a couple extra digits here. We've got 3 sig figs. So if we take those number of moles and we divide it by the volume, now we know the moles, we know the volume, here 1.50 liters, we should get the molarity. So quick calculation, 0.177 big M here for molarity. So we can also use molarity in calculations. So let's do a problem where we use molarity in calculation. Just give you a quick example. So let's say we want to determine how many grams of sucrose, and sucrose is C12H22O11, this is table sugar, are contained in 1.72 liters of a 0.758 molar sucrose solution. Okay, so we've got 2 relationships here. We've been given, we're going to need a molar mass conversion. So mole to grams, because the question is how many grams of sucrose. And then we have this molarity, which will basically get us from liters to moles. That's what molarity is good for. So let's set up this problem. Now we can do a little side work here. This is going to be 342.34 grams in terms of that molar mass there. Okay, so 1.72 liters of solution. We are going to use the molarity. The molarity is 0.758. That just means that there is 0.758 moles for every 1 liter, right? That's what molarity means. It's moles over liters. We can calculate it with any number of moles and any amount of liters, but just like percentages, we can take a percentage and use it as a conversion factor. We can do the same thing with molarity. We're just going to make this that many moles over 1 liter. So this will get us from liters of solution into moles. And then we have the molar mass, that 1 mole of this sugar is 342.34 grams. And that's the only conversions we need. Liters of solution goes away, moles goes away, and quick calculation should reveal about 446 grams of that sugar. Okay, let's get back to our topic now, ion concentration. So the reported concentration of a solution containing molecular compounds actually reflects that concentration. So for example, a concentration of 0.1 molar of sucrose, C12H22O11, right, would actually have 0.1 moles inside 1 liter of this stuff. But a 1 molar solution of calcium, or a 0.1 molar solution of calcium chloride, for example, would actually have more moles of ions than it would, or total moles of substances than that first one would. And this is because this guy here dissociates into 3 ions. It dissociates into a calcium 2 plus, a chlorine minus, and another chlorine minus. And so the overall concentration of ions would actually be whatever this concentration is times 3. And so that's the case whenever we're dealing with ionic concentrations. It actually, the concentration of individual ions present in solution can be approximated from that overall concentration, but it's only an approximation because some cations and anions actually pair up again. And so, when some of these are repairing up, then our numbers are always going to be a little lower than what we would expect. Now let's do a practice on this. So let's say, let's determine the molar concentrations of Na plus and PO4 3 minus in a 1.5 molar Na or sodium phosphate solution. So what can help is to look at how this thing dissociates. So I'm going to write Na3PO4 aqueous and show it as its ions, so kind of like a total ionic. So this would be 3 Na plus ions, and it would be 1 PO4 3 minus ion. So if the concentration of NaPO4 is 1.5, then it makes sense that the concentration of PO4 would still also be 1.5, right? Because every molecule only comes with one PO4 in it. But every molecule comes with 3 sodiums, and so 1.5 molar of this molecule ends up being 4.5 molar of the ions, because there's 3 times as many. And so that's how you go about kind of figuring this stuff out. You have to look at the balance for the correctly written formula. We could do another one real quick. Calcium chloride. So you have a 0.75 molar solution. What are the molar concentrations of each of these? So pause it, give it a shot. I'll tell you the answer in 3, 2, 1. For calcium 2 plus, the concentration is going to be approximately 0.75. For the Cl minus, the concentration is going to be double that, because there's 2 for each one of those. The total ion concentration, so total ions concentration will be 2.25 molar, right? And up here it would be 6 molar, because total ions, we would just add those all together, because it's moles over liters, so it would be moles of ions. Well, 4.5 moles and 1.5 moles is 6. Okay, so that's ion concentrations. Let's talk about solution dilutions. So solutions are often stored in concentrated forms called stock solutions, and many lab procedures call for a less concentrated solution, so chemists must dilute the stock solution. This is done by combining a certain amount of the stock solution with water. So to determine how much of the stock solution to use, the dilution equation M1V1 equals M2V2 is used. Now, M1 and V1 are the molarity and volume of the initial concentrated solution, and M2V2 are the final diluted solution. Now, this equation works because the molarity multiplied by the volume gives us number of moles. This comes from our big M equals moles over liters equation, right? Where liters, let's think of it as volume. To get moles by itself, we just go M times V, right? So this works because M times V is moles. Now, because both solutions have the same number of moles, then these M times V's are equal to each other, okay? This doesn't work with stoichiometry. This only works with solution dilutions, okay? One quick thing to mention, always add acids to water, never water to acids. And this is because when you have a cup of water and you pour acid in it, sometimes there's some splash out, and the splash out would be water that's coming out because you added acid. If you did it the other way and you added water to acid, the splash out would be the acid coming out of the cup, and so you want to be careful. Let's do a dilution. So M1V1, M2V2. Let's say that we want to prepare a 5-liter solution of a 1.5 molar KCl solution. So 5-liter, 1.5 molar KCl solution, and we want to make it from a 12 molar stock solution. So the question is going to be, how much do we take and how much water do we add? And we'll get over we'll do both of these together. So our M1 in this case is going to be 12 molar. Our V1 is what we don't know, because we're given M2 as 1.5, and we're given V2 as 5. So we're going to solve for V1. So you do some rearranging here, right? So V1 is going to equal M2 V2 over M1. If we plug in all of our values for this, we're going to find that V1 is equal to 1.5 times 5 over 12. So V1 is 0.625 liters. So this is just telling us how much of our stock solution that we want to grab. Now we want to make a 5-liter solution at the end, so we're going to have to add water to that. So in addition to the 0.625 liters of the stock KCl, we're going to have to add some amount of water to reach an ultimate volume of 5. So 5 minus 0.625 is going to be 4.375. So that's how much water we would need to add in terms of liters. So this is a typical solution dilution problem. Now I like to do chain dilutions, meaning I would give you a stock solution, have you dilute it once, and then have you dilute it again. And all that means is that you're going to do M1V1, M2V2 twice. Right, you'd find the new concentration of the second solution. And then if you take some of that, that's going to be V1. This would be M1 again. And then you could find, I guess we could call this M3, and this M2. So yeah, chain dilutions are something that you can do. There are some problems in the book that I recommend you try. All right, solution stoichiometry. So solution stoichiometry is just like regular stoichiometry that we've been doing in Chapter 8, just like the stoichiometry we did in Chapter 11 with gases, only now we are doing it with solutions. So each reaction involving aqueous reactants and products, it's often convenient to specify the amount of these reactants or products in terms of their volumes and concentrations, kind of like we did with volume, temperature, and pressure with the gas chapter. We can use volume and concentration to calculate the number of moles, right? M times V, and then use the coefficients, the stoichiometric coefficients, to be able to relate moles to each other. So general solution map would look something like this. Volume of A would give us moles of A, which we would relate to moles of B, and we find volume of B, something like that. Let's do an example. Let's take H2SO4, let's add NaOH to it. These are the reactants. Products would be Na2SO4, H2O. Pause the video, take a minute, balance it. 2 sodium hydroxides, 2 waters. We need a balanced equation for this to work. I left the phases off. We don't need the phases here. It doesn't matter. So how much 0.125 molar sodium hydroxide do we need to actually completely neutralize 0.225 liters of this 0.175 molar sulfuric acid? Now we know that acid-base reactions neutralize each other, so you have to have the same amount of acid as base. So here we are given the volume and the molarity of our H2SO4. Using that, we're going to be able to find out how many moles we have. So let's kind of do the setup here. So we're going to start with 0.225 liters of H2SO4, and we're going to use our molarity as a conversion factor. Molarity is 0.175, so that means 0.175 moles of H2SO4 is in 1 liter of H2SO4. So this is going to cancel. You'll see the liters of H2SO4 unit. So then we go to our equation. This equation here says that every 2 moles of sodium hydroxide will cancel out 1 mole of H2SO4. So we need to put 1 mole H2SO4 on bottom, 2 moles NaOH on top. This cancels out our moles H2SO4 unit. Remember, we're ultimately looking for how many liters of sodium hydroxide we need. So now we have moles of sodium hydroxide from our balanced equation. So we're going to need to convert from moles to liters again, this time in the other direction. Instead of liters to moles, we're going moles to liters. So we're going to put our conversion factor upside down. We're going to say that there's 0.125 moles of NaOH in every 1 liter NaOH. This cancels our moles NaOH unit, and now the only one left standing is the liters NaOH. Quick calculation will show 0.630 liters NaOH was needed to completely react with that amount of sulfuric acid. All right, so let's do one more. So let's determine the amount of, we can keep using acid base because I think that one's a little easier to kind of wrap our minds around. So let's go NaOH, again reacting with, let's make it HCl to make NaCl and H2O. And let's give us, let's say that the volume of sodium hydroxide is 0.15, sorry, we want volume. How much sodium hydroxide is needed to react with, let's say, 25 mils of 0.055 molar HCl? So again, we're going to say we're going to start with our volume of HCl, because we need this as a conversion factor, molarity. So we're going to say 0.025 liters of HCl. Our conversion factor says that for every 1 liter HCl of this concentration, that there is 0.55 moles of HCl. Our balanced equation says, and this is balanced, that there's 1 mole of HCl to every 1 mole of NaOH. And at this point, right, units are canceling. HCl's canceled, moles of HCl's canceled. We're at moles of NaOH. We have a concentration. We know that there's 0.150 moles of NaOH inside every 1 liter of NaOH. And this is because we know the molarity. Moles of NaOH cancels. We can calculate this. 0.025 times 0.055 divided by 0.15. So this would be, we would need 0.0091 liters, or 9.1 milliliters. So 9.1 milliliters to react with 25 milliliters. Now, does that make sense? Yes, because the 9 millimeters was a higher concentration than the 25 milliliters. So that makes perfect sense. All right. So freezing point depression. So this was the problem we did. So freezing point depression, let's talk about that. So there are a couple of properties called colligative properties. And colligative properties are those that depend on how much solute you have. So they're things that, they're like freezing point depression and boiling point elevation, changes to a solution's freezing point or boiling point, or at least the pure solvent's freezing point or boiling point, because you've made a solution. And depending on how much solute is there, is what we would is going to determine the extent of the difference or the change. And these are called colligative properties. Now the first is the freezing point depression. Now the freezing point of a solution containing a non-volatile solute is always lower than the freezing point of that pure solvent. And for freezing point depression and for boiling point elevation, the concentration of the solution is usually expressed in molality. Molality, it's a little m instead of a big M. And now molality is the number of moles per solute, moles of solute per kilogram of solvent. So you'll notice that this is volume independent. So volume doesn't matter here. It's all about the weight of the solution. So it's the kilograms of the solvent also. So weight of it as opposed to volume, but it's also of just the solvent and not the solution. So it's slightly different than what you're used to. Let's calculate one real quick. Let's say that you are given 17.2 grams of C2H6O. O2. This is, I don't know what this is. And this is ethylene glycol. This is antifreeze. And let's say that it's dissolved in 0.500 kilograms of water. So we would need to figure out the molality of this. So we would need the moles. So I'll give you the molar mass for this guy. The molar mass is 62.08 grams per mole. And so we'd say 17.2 grams, 62.08 grams per mole is going to be 0.2771 moles. Too many sig figs, but that's okay. So if we know how many moles, then we divide it by the kilograms of solvent. In this case, it's a nice easy number, 500 kilograms. And also in this case, they're giving you the kilograms of the solvent. You could be given liters, you could be given gallons, and you'd have to do some converting. So this was a nice problem. And then a quick calculation here reveals that it is 0.554 molal. Molal is how we say it, as opposed to molar. Okay. I often like to give you just a set of information and then say calculate the mass percent, calculate the molarity, calculate the molality, and see if you can do it. And you'll have all the tools you need. You'll have all the different equations you need. It's just, figuring out which one to use where. Let's actually do a problem. So let's look at let's calculate the freezing point of a 1.7 molal ethylene glycol solution. So this is that antifreeze solution. So ethylene glycol, I don't remember the formula, C2H6O2 or something like that. You were given the molality, 1.7. Now here's the formula. So the formula says that we're going to find out what the change in the freezing point is if we know the molality and something called a freezing point depression constant. Now we have to have the constant, and that's always given for whatever solvent you're using. Now in our case here, the freezing point depression constant is going to be for water, and for water it is 1.86 degrees Celsius per kilogram solvent per mole solute. So there's some units there. So we would just need to come in here and plug in, the math. Do the 1.7 molal times the Kf. Now, if we do this, we find out that the temperature drop is going to be 3.2 degrees Celsius. So this is going to go down by 3.2 degrees Celsius. Now, I'm sorry, there's no minus here. 3.2 degrees is the change in temp. Now, the question here, though, wanted to know what's the freezing point of this solution. We would then have to say, well, what's the normal freezing point of water? 0. So then now it's gone down by 3 degrees. So what's 0 minus 3.2? Minus 3.2. So the new freezing temperature of this solution is negative 3.2. If we make this concentration even higher, this temperature drops even more. If this concentration was nothing, if there wasn't any, if it was really, really little, then this number, this difference gets smaller. And so then it would be closer to 0. This is how antifreeze actually keeps your car from your internal liquids in your car from freezing, right? When it gets too cold outside. It's because it's a really high solution of this sugary substance. This actually prevents certain frogs from being able from freezing all the way through, during the winter when they hibernate. Their blood contains a lot of sugar, and it just keeps it from freezing. The boiling point of a solution containing a non-volatile solute is also higher than the boiling point of a regular solution. And so for automobiles and antifreeze, right, not only keeps your car from freezing, the coolant from freezing, but it also keeps the coolant from boiling away, especially when you're driving around in a hot temperature. So the boiling point elevation equation is very similar to the freezing point depression constant. We get a change in the temperature measured by molality times, in this case, a constant. And this for the boiling point constant, it is 0.512 as opposed to the previous number. So 1.86 and 0.512 are numbers that that are on your formula sheet, but you'll need these for this type of equation. So let's do boiling point for the same solution. So let's say that I have a 1.7 molal ethylene glycol solution, and I want to know what the new boiling temperature is going to be. So if we plug that in, 1.7 times 0.512, we get the change in temperature is 0.87 degrees Celsius. So what's the new temperature that it boils? Well, what's the old temperature it boils? Water boils at 100 degrees Celsius. So 100 degrees plus 0.87 degrees is going to be 100.87 degrees. So, of course, if we want to be able to use those sig figs, we need to put more sig figs there. So that's how we would use these types of equations. Now, there is one more effect of colligative properties. Sorry, I'm getting blown up here by my front door. And that's called osmosis. Now, osmosis is the flow of solvent from a less concentrated solution to a more concentrated solution. So this occurs when a solution containing a high concentration of solute actually draws solvent away from solutions containing a low concentration of solid. And this is because nature wants to balance things out. It doesn't like having high concentrations. It wants to dilute everything, and so water is going to flow to wherever it needs to dilute something. Now, this is a problem if you're out stuck at sea and you're thirsty, because if you drink some seawater, that salty water in your intestines is actually going to draw water into your intestines as opposed to letting water flow into your body. This is actually going to dehydrate you even more, so it's no good. In an osmotic cell or osmosis cell, water flows through the semi-permeable membrane from a less concentrated solution to a higher one. And as a result, fluid rises in one side of the tube until the weight of that excess fluid sort of creates enough pressure to stop the flow. Now, osmotic pressure, like freezing point depression and boiling point elevation, is a colligative property. So it depends only on the concentration of solute particles, not the type of particle. The more concentrated the solution, the greater the osmotic pressure. And the membranes of living cells act as semi-permeable membranes. So if you put a living cell into seawater, it loses water through osmosis and becomes dehydrated. And I've got some pictures here. So a solution that's a solute concentration of the surrounding fluid that's equal to that inside the cell has no net flow of water, and so these are what normal cells look like. If you place a cell in pure water, then the concentration is too low on the outside of the cell, and so water flows into the cell because it's more concentrated inside and can burst the cells. And the opposite, if you place it into a concentrated solution, osmosis actually draws water out, called crenation, and crenates your cells, and this can lead to them popping and getting messed up as well. All right, so solutions that have osmotic pressures equal to that as the body are called hypoosmotic. Solutions that have osmotic pressures that are greater than body fluids are called, if they are less pressure, they're called hypoosmotic. If they're greater pressure, they're called hyperosmotic. And if they are the same pressure, like intravenous solutions need to be, then they're called isoosmotic. And as an example, when a patient is given an IV in a hospital, the majority of the fluid is usually an isoosmotic saline solution, a solution containing about 9 grams of sodium chloride per 100 mils of water. All right, so in this chapter we looked at solutions, we looked at how to define them, we looked at solid liquid solutions, gas liquid solutions, and how they are affected by temperature, and in the gas liquid solution case, pressure. We looked at solution concentration and the ways that we express that, mass percent, molarity, molality. We looked at solution dilution, and we looked at freezing point depression and boiling point elevation. I recommend you guys give those practice without water as a solvent. Find some problems where like cyclohexane or a different solvent is actually a different solvent other than water, so that you get different Km and Kb values and different boiling points and freezing points, and see if you can still understand the concept there. And then we looked at osmosis. Hopefully these learning objectives help, and as always, please utilize the discussion board and sending me emails. This lecture should help you with the Solutions and Solubility Lab, but that's about it. All right, guys, I'll see you in the next video.